In the last two classes, we have seen what spectroscopy is, what are the energy levels present in a molecule, different molecular energy levels we have seen. Now here, today, we'll see what is happening when the molecule is irradiated with a radiation, or what is the exact interaction that's happening in the molecule. And also we'll see the different spectroscopic techniques. Now we know that spectroscopy is the study of the effect of interaction between electromagnetic radiation and matter. And so when a molecule or a sample is irradiated with light or electromagnetic radiation, either emission will happen or absorption will happen. And the spectroscopic studies related to emission is called emission spectroscopy, and that related to absorption is called absorption spectroscopy. And we know that the electromagnetic radiation which we use is associated with oscillating electric field and magnetic field, which are perpendicular to each other, and both of these are perpendicular to the direction of the radiation. We have seen this also. Now, when a sample is irradiated, it will interact with the either with the electric field component or with the magnetic field component of the radiation. Now this interaction with the radiation, with either the electric field or the magnetic field of the radiation by the sample, will result in the change in energy of the sample, or it can be the absorption of the energy of the radiation by the sample. Now, we know that the radiation of the energy of the electromagnetic radiation is quantized. So when there is absorption, that also must be quantized. Let's see that, how it is and what is the quantity. Now, if we just depict the energy levels which we had written earlier, we have the lowest energy level, take it as E1, and another next higher energy level E2. So when a sample is irradiated with electromagnetic radiation, energy of the sample increases from E1 to higher energy E2, and that's called absorption. So when the sample absorbs energy from the molecule, from the radiation, it goes from higher energy level to, lower energy level to higher energy level. Similarly, if the molecule gives off energy, comes down to lower energy level from higher energy level, it will emit some amount of energy or some amount of radiation, and that phenomenon is called emission. Now this absorption and emission happens, will be happening if the difference in energy level is quantized. Okay, so and that is delta E, the difference in energy level. And that is given as E is equal to h nu. So that quantization is necessary. And we can also say that a molecule can absorb a particular frequency only, or absorb a radiation of a particular frequency or wavelength only if there exists within the molecule an energy transition of the magnitude delta E equal to h nu. So this energy difference between the different energy levels must be h nu, quantized. Okay, and this assumption, or this is called the Bohr condition for spectral transition. So the Bohr condition for spectral transition is that if the molecule is to absorb a radiation of a particular frequency or wavelength, the energy transition, the difference in the energy transition must be quantized and must be equal to h nu. And here h is the Planck's constant, and nu is the frequency of the radiation. It can be related to wavelength. You can put it as hc by lambda. We have seen this in our earlier videos. Now, if the absorption or emission happens, the frequency of the wavelength absorbed, or the frequency of the or frequency or wavelength of the radiation absorbed, or frequency or wavelength of the radiation emitted can be recorded, and that instrument is called the spectrometer. And the spectrum which comes out of the spectrometer when this is recorded is called absorption spectrum or emission spectrum, depending upon which frequency or which wavelength is the spectrometer recording. And the nature or the style of the spectrum, the pattern of the spectrum will be something like this, depending on the parameters which we are plotting. Say for example, if you're plotting the absorbance against the wavelength of the radiation, then the plot which we get will be some of this pattern. This is the absorption spectrum pattern. Okay, when we plot absorption against wavelength. And if we plot percentage transmittance against wave number, then the plot will be something like this, and this is the emission spectrum. So usually to plot the absorption spectrum, we plot absorbance against wavelength, and to plot emission spectrum, we plot percentage transmittance against the wave number. And the width, height, etc. of these plots depends upon the molecule, the structural parameters of the molecule. So every molecule will be having its own specific type of absorption spectrum or emission spectrum. And the spectrum will give us information regarding the structural structure of the molecule. And one more thing which you need to remember is that the absorption spectrum of a species will be complementary to its emission spectrum. And hence, both absorption spectrum or emission spectrum will give us the same information. So we need to study either of these, either the absorption spectrum or emission spectrum of the molecule. Now we'll see which are the different types of spectroscopic techniques present, or which we use. Now, one of the spectroscopic technique which we use is the microwave spectroscopy or rotational spectroscopy. In this spectroscopy, we use the microwave radiation or the radiation in the microwave range in the electromagnetic spectrum to radiate this sample, or in microwave spectroscopy, we study the interaction of the molecule matter with microwave radiation. And this causes transition in the rotational energy, transition between rotational energy levels in gaseous molecules, which possess a permanent dipole moment. So the rotational spectrum will be provided with molecules which has a permanent dipole moment. So not every molecule will give us a rotational spectrum or will respond to rotational spectrum or rotational spectroscopy or microwave spectroscopy. Only those molecules which possess a permanent dipole moment will respond to microwave spectroscopy. So the characteristics of microwave spectroscopy are: the radiation used will be in the microwave range. The transition happening will be between rotational energy levels. The molecules which we use must be in the gaseous phase, and the molecules must possess a permanent dipole moment. Another spectroscopy is the vibrational spectroscopy or infrared spectroscopy, and sometimes it is also called as vibrational rotational spectroscopy. Now, in this, as the name suggests, we use the radiation in the infrared range to irradiate the sample, and the transition will be happening between the vibrational energy levels of the molecule. And one more thing which you must know is that the mode of vibration is accompanied by a change in the dipole moment of a molecule. There will be a change in the dipole moment of the molecule if we irradiate the molecule with radiation in the infrared region. Only if there is a change in the dipole moment of the molecule will we get a spectrum. That's important. Okay, so to get a spectrum, infrared spectrum, there must be a change in the dipole moment of the molecule. Okay, and the next spectroscopy which we have is the Raman spectroscopy. and it is concerned with both vibrational and rotational transitions. But the difference is that here the Raman spectroscopy deals with the scattering of light. It's not related to the absorption, it's related to the scattering of the light when visible light is incident on a sample. So the pattern of scattering is studied in Raman spectroscopy. Okay, and another spectroscopy is the electronic spectroscopy or the UV visible spectroscopy, ultraviolet visible spectroscopy. So the transition is happening between the electronic energy states and it is caused by the absorption of the radiation in the ultraviolet or visible region. So that's why it's called UV visible spectroscopy. The other two spectroscopic techniques are NMR spectroscopy and ESR spectroscopy. Now in these two techniques, the sample is placed either in a magnetic field or an electric field and its changes are studied. Now in NMR spectroscopy, the transitions induced between the spin energy levels of certain nuclei in a species in an applied magnetic field by absorption of electromagnetic radiation in the radio frequency region is studied. Okay, so in NMR, we place a sample in the in an applied magnetic field and absorption of the electromagnetic radiation in the radio frequency region are studied. In ESR spectroscopy, the transitions induced by the absorption of the radiation in the microwave region is studied between the magnetic energy levels of an electron with the unpaired spin in electric external magnetic field. Okay, so the transition or the transition happening between the magnetic energy level of an electron with unpaired spin in an external magnetic field are investigated when the sample is irradiated with radiation of the microwave region in ESR spectroscopy. We will be discussing in detail regarding few of these spectroscopic techniques. Now to understand the various spectroscopic techniques, we need to go for an approximation called the Born-Oppenheimer approximation. Now in Born-Oppenheimer approximation, the assumption taken is that, or you can say that they consider for this approximation the difference in the weight of the nuclei and the electrons are considered. Now we know that nuclei is much heavier than electrons, and hence in Born-Oppenheimer approximation they assume that since the electrons move very fast than the nuclei, the movement of nuclei can be almost considered as static, or we can assume that the nuclei does not move, it is the electron which moves. So we can say that all the spectroscopic transitions happening is mainly due to the movement of electrons from one energy level to another energy level. Now we know that the energy of a molecule is associated with or is the total sum of different energies, and to understand spectroscopy, we need to consider three types of energy. Among these, they are the electronic energy, vibrational energy, and rotational energy. And all these energies are quantized. And the electronic energy is having higher energy than vibrational energy, and then comes the rotational energy, which has the lowest energy. So the difference in transition will also be of the same order. The order of separation between quantized state of these energy is that electronic separation is greater to vibrational separation to rotation separation. This we have seen in the molecular energy diagrams. And the total energy of the molecule or sample is considered to be the total of all these energies, and the difference will also be considered to be the difference of all these energies put together. So this, keeping in all these Keeping all these in mind, we'll go further to study the spectroscopic